Hi everyone. In this lecture, we will be looking at the network core, and we'll start discussing mainly about packet switching and circuit switching. In the previous lecture, if you recall, we looked at the network edge and we looked at the end systems, mainly the hosts that make up the internet. We also looked at the access networks to which the different hosts connect to, and we had a brief discussion of the physical media that is used to connect the different hosts in the internet. Today we'll move on and look at the network core, and then we'll talk about two important paradigms called packet switching and circuit switching. But first, what is the network core? The network core consists of a mesh of interconnected routers. So in this figure, the routers in the two blue networks that you can see constitute the core of the internet. And what they do is they help to carry packets from the source to the destination. So for example, let's consider that through your phone, you're trying to access the website of google.com. Now, the server of google.com is going to serve you the data that you requested for, but what it's going to do is it's going to divide this high level application layer message into smaller network level packets. These network level packets are then going to traverse the internet and then move from the server of google.com to the client, which is the phone here. What these routers do is that they forward packets from one router to the next such that the packet moves closer to the to the destination. For example, here the source is basically the server of google.com, which is trying to send you the web page of google.com, and the destination is your client, which had requested the web page. What the routers in the internet would do is that they would move these packets closer to your would help move these packets from the server to you. Now each of these packets is going to be transmitted at the full capacity of the links connecting these intermediate routers. So now to carry this data from the source to the destination, the paradigm that's used in the internet today is a circuit switch model. Is a packet switched model. In a packet switched model, what the entire message, as I mentioned before, is divided into smaller packets, and each of these packets is carried from the source to the destination. What the routers or the intermediate routers do is that they store each of these packets and then forward it to the next router, and this process continues till the packet reaches the host which had requested the message. Now, let's try to analyze how this packet switched paradigm is going to work. Let us assume that there are L bits in a packet. Now, to transmit a L bit packet over an R bit cable, it's going to take R over L over R time units, because L bits divided by R bits per second, which is L over R. Now so in this figure here, as you can see, there are two hosts which are connected by this router in between, and we are trying to move a packet from one of the hosts to the other host. Now to transmit it for the first R bits per second link, the time that is going to take is L over R. Now to move it to the next R bits per second link, it's going to take another L over R time. So the total time to move a packet from one host to the other is 2 times L over R. This is the total transmission delay that's going to take place to get the packet from one host to, which is the source, to the other host, which is the destination. So let's look at a numerical example to understand this concept of delay. So let's assume that the packet that is going to be transmitted is 7.5 megabits, which is 7.5 to the times 10 to the power 6 bits. And the rate at which packets can be transmitted over the wire is R, which is 1.5 megabits per second. To get the delay over one of these links, to get from say one of the hosts to the router, it's L over R, and if you do L over R, it's going to give you 5 seconds. So that is just the one hop transmission delay from the source to the router. Now, as I just mentioned, the end-to-end delay is 2 times that, so the end-to-end delay is going to be 2 times 5 seconds, which is 10 seconds. Apart from the the delay that I just mentioned, which is the transmission delay, packet switching also incurs other kinds of delay, which is, well, the one example is a queuing delay. So let us assume that there is a queue at every router and packets are coming into the queue. You can think of these packets as one classic example of a queue is a queue at a bank. So you can think of these different packets as human beings that are entering the queue at a bank and say at a teller to get whatever to get money from the bank. So each of these packets experiences a delay while other packets are getting processed. So, for example, you go to the bank to a teller to withdraw money, and if there are some people already in the queue ahead of you, they have to be processed, and only then your request is going to be processed. The amount of time that you spend waiting in the queue for other customers to be served in case of the teller is basically the queuing delay. It's similar here. Here in the router, in case of the routers, as you can see, there is a green packet and there are green packets and red and blue packets. The green packets, when the first blue packet enters, there are already two green packets in the queue. So only after the two green packets have exited the queue will the blue packet move out of the queue. So that is the queuing delay. Now, so this is going to add to the total delay that it takes for a packet to reach from a source to a destination. We'll come and discuss delays in greater detail in the next lectures. Another important thing that we have to take care of or study here is loss. Let's assume that the queue has a fixed capacity. So here, let's assume that the queue has just four has a capacity of 4. That is, it can only store 4 packets. So in this example, the router connected to A and B is already holding 4 packets. Now, before those once one of those packets is actually put onto the wire, if additional packets enter, there is no place for the router to hold those packets. So those packets are going to be dropped. Now, if those packets are dropped, there is no way to recover those packets, and though that causes a loss. So there in the internet, while using the internet, you can experience loss, and that mainly happens because of queues overflowing and they do not having enough capacity to accommodate all the packets that are coming to them. We'll study delays and loss in greater detail as we move on. Now, the two important network core functionalities that happens in a packet switch network are routing and forwarding. So what is routing and forwarding? Routing is simply determining the path between a source and a destination. Let's look at an example here. Say you want to travel from Boston to San Francisco. To travel from Boston to San Francisco, you have to determine the intermediate towns. And say you want to do this road via road. So you have to determine the intermediate towns where you're going to stop for the night. And so this entire route that you take from Boston to reach San Francisco through the intermediate towns, that is the route. Similarly, in the internet, when a client is requesting some data from a server, the data from the server has to be gotten to the client, and that has to take place over a large number of routers. And the path to which this data flows to the client from the server is actually determined using our routing algorithm. There's another aspect or another function of the network core, which is basically forwarding. Forwarding determines how packets are going to be forwarded. So here, what the routing algorithm is going to do is it's going to determine if a router has multiple links, which link a particular packet should go through. So let's consider this routing table for the router which output interfaces are marked as 1, 2, and 3. Now what it says, we'll come to this in detail. What it says is certain packets are going to go through 3, some other packets which have a different header value are going through output link 2, and so on. So now a packet comes in with, say, a value in the header 0111. As you can see from the table, 0111 is outputted on the link or output link 2. This functionality of how to how to transmit or forward packets based on the header information is called a forwarding function. So routing is the high level idea of determining a route between a source and a destination, and forwarding is the decision taken at each of the intermediate routers on how this packet is going to be forwarded. So an alternative approach to packet switching is actually circuit switching. So in circuit switching is very common in a telephone network where the entire resources from end to end have to be reserved before any data can be communicated. So for example here, in a circuit switch network, the two, there are three there are three hosts, as you can see, and the two hosts at the two diagonal ends have reserved a connection marked in dark green, or have reserved the entire resources marked in dark green, and then they can transfer the data that they want to. In a circuit switch network, first there is no sharing. The entire end-to-end resource has to be first allocated before data can be transmitted. It gives the circuit-like behavior. So it's used in a telephone network, especially in the landline that you have in your home. What happens is the entire resource, or the amount of, and in this case the resource is basically the bandwidth that is needed to transmit your call from your phone to the phone that you're calling to, is first reserved, and then you're allowed to communicate with the other person. So it is used in telephone networks, and it is not prevalent in the internet. And the internet is usually packet switching that takes place. The two methods to implement circuit switching are frequency division multiplexing and time division multiplexing. So as I just mentioned, in a circuit switch method, what happens is you have to allocate resources between the two hosts which have to communicate. One method is and so this resource has to be allocated. The first is, what is this resource? The resource can either be some time or can be frequency. So in FDM, what happens is the entire frequency is divided into different bands. And for example, there are the entire frequency spectrum is divided into 4 segments, and each of these bands is allocated to a different user. So for example, you can have the pink user using the band at the bottom, while the blue one is using the one at the top. In time division multiplexing, then the frequency that is the resource that's available is time, and that is divided among different users, as you can see in this animation. So once this entire resource has been allocated, only then data or communication can take place. The biggest advantage of circuit switch networks is that once a connection has been established, the entire connection, the entire resource is allocated to it. There is no sharing of resources. So let's look at an example to understand the difference between packet switch and circuit switch networks. For example, let's assume that in this example there are n users which are using this 1 megabits per second link. Now what we want is each user wants 10 kilobits per second when they are active. And let's assume that they are only active 10% of the time. So whenever the users are active, all these users are going to get 100 kilobits per second.